Have you ever wondered if the very act of observing something could fundamentally change its nature? In our everyday world, observing a book on a shelf does not change the book. But at the tiniest scales of reality, things are vastly different. The quantum measurement disturbance effect is a fundamental principle in quantum mechanics, stating that the act of measuring a quantum system inherently alters its state. This means you cannot probe a quantum particle to discover its properties without disturbing those properties in the process. The core reason for this effect lies in the nature of quantum states. Before measurement, a quantum particle often exists in a superposition of multiple possible states. Think of an electron spinning both clockwise and counterclockwise simultaneously. When a measurement is performed, the quantum system is forced to choose or collapse into one definite state. This collapse is not due to a clumsy instrument or an imperfect scientist. It is a built-in feature of quantum reality itself. This disturbance is particularly pronounced when trying to measure what are called non-commuting observables, like an electron's position and its momentum at the same time. The more precisely you measure one, the less precisely you can know the other, which ties directly into the Heisenberg uncertainty principle. Every measurement interaction, no matter how gentle, involves an exchange of energy or information between the measuring device and the quantum system. This interaction invariably perturbs the delicate quantum state, causing it to transition from a probabilistic superposition to a single, definite outcome. It is a direct consequence of the wave-particle duality, where the act of measurement forces the system to behave as a particle, collapsing its wave function. For scientists and engineers working with quantum systems, understanding this effect is crucial for designing experiments and developing quantum technologies. It means that information about a quantum state must be extracted carefully, recognizing that the act of observation changes what is being observed. Researchers employ techniques like weak measurements or quantum non-demolition measurements in specific contexts to minimize this disturbance, though it can never be entirely eliminated for all properties. This profound principle is what underpins a key aspect of quantum cryptography. If an eavesdropper attempts to measure or observe the quantum state of a transmitted photon, their very act of measurement will disturb its state. This disturbance provides an immediate and undeniable signal to the legitimate communicators that their transmission has been tampered with. This ensures the security of quantum key distribution protocols. It is a truly unique feature of the quantum world, showing that observing is not a passive act. Ultimately, the quantum measurement disturbance effect highlights the deeply counterintuitive nature of quantum mechanics compared to our classical experiences. It is not a flaw to be overcome but, rather, an intrinsic characteristic that defines how quantum information is processed and how quantum systems behave. Grasping this concept is essential for truly understanding the limits and potential of quantum technologies.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.